In the name of Almighty God, I am Master Sankoshi, and today I want to talk about the electricity and magnetism from the physics GRE. According to ETS, approximately 18% of the exam covers electromagnetism. Given the format of the example, the questions change to emphasize a broad set of topics in electricity and magnetism rather than deep theoretical issues or analysis of complicated charge configurations. You will, for example, find plenty of AC and DC circuits in addition to the more traditional topics of electro and magnetic statics, induction, Maxwell's equation, and electromagnetic waves. The general philosophy that you should take away from this chapter is that electromagnetism is conceptually simple. There are only a few key concepts such as symmetry and boundary conditions, most of which are buried somewhere in Maxwell's equations. The vast majority of the work lies in the figuring out how to apply these basic ideas to specific configurations. The key to success on the electromagnetism problems on the GRE is to develop enough intuition with a few specific classes of problems that you can quickly deploy the necessary equations to solve them. We will try to outline the general ideas concisely and try to illustrate how to choose the fastest methods for the common classes of problems. The first section is 2.1 electrostatics. Electrostatics refers to problems where charges and fields are not moving or changing in time. If you have a configuration of charge that doesn't change in time, electrostatics lets you calculate resulting electric fields and forces. We will generalize these to include time dependence in section 2.3. Now I want to go through the subsection of electrostatics, which is 2.1.1 Maxwell's equation for electrostatics. The tools needed for analyzing electrostatics problem are very simple. In fact, it just boils down to the first two of Maxwell's equation in free space in the absence of magnetic fields. The first one is delta E is equal to rho divided by epsilon 0. The next one is delta multiplied by E is equal to zero electrostatics. The first equation actually holds true regardless of whether a magnetic field or time dependence is present, but the second is only true in electrostatics. These two equations tell you how to build the electric field E from the charge distribution rho. To figure out how a test charge Q moves in response to an electric field, you need one more equation. FA is equal to QE. That's it. In principle, you can solve for any static electric field with these equations and they compute the motion of a particle in the field. Given knowledge of a charge distribution, as you are probably well aware, however, partial differential equations are almost always quite nasty to solve, so we use a few additional tools to calculate the electric field in practice. Now I want to go through the another subsection 2.1.2 electric potential. The first tool is the scalar electric potential. Under some fairly general conditions, the fact that delta multiplied by E is equal to 0 implies that there is a scalar potential field, which is a VR, which we also call the electric potential, such that E is equal to minus delta V. This is still electrostatics since the field isn't moving, only the test charge whose field we don't care about in this context. This can be integrated to give voltage in terms of the field of voltage. VAB is equal to minus the integral, the lower bound is R, the upper bound is BE, the differentiation I, which hopefully looks familiar from potential energy in mechanics. Here the point R has been defined as the zero of potential, as is the case with the potential energy in classical mechanics. Electric potential must always be defined relative to some reference location for electrostatics problems unless otherwise specified. The reference point is often taken to be infinitely far from the location of interest. As with potential energy in mechanics, minus sign, there is a relative minus sign between the electric field and the electric potential, which is easy to forget. Also note that V is not a potential energy, rather it is potential energy per unit charge, and the real potential energy of a particle of charge q in a region which electric potential V is equal to U is equal to QV because it is proportional to the true potential energy. The electric potential is also only defined up to a constant. So changing V by constant value doesn't change the value of the electric field, thus it is only differences in potential that we measure. Finally, since the potential VR is a scalar quantity, not a vector like the electric field, it is sometimes easier to calculate the potential for a particular charge configuration and then convert to the electric field. For practical purposes, both contain equivalent information. At this point, we should mention the fact that both E and V are additives. Maxwell's equations are linear differential equations, so to find E or V of several charges, you should just add up using vector addition in the first case or ordinary addition in the second, the corresponding E and V of the individual charge. The second tool for solving electrostatics problem is the direct solution of Maxwell's equations. If we plug into the 2.1, we obtain the single scalar equation as delta to the power of 2v is equal to minus rho divided by epsilon 0. Now, as a Poisson equation, often we are asked to solve this equation in a region where the charge density rho is zero, in which case it reduces to Laplace equations. Delta to the power of 2 V is equal to 0 empty space. We can write the general solution to Poisson's equations as an integral over the charge distribution rho r. Vr is equal to 1 divided by 4p epsilon 0 integral rho r prime divided by r minus r prime d to the power of derivative to the power of 2, or the third order of the derivations are pre. Note the variables carefully. R labels the point where you are measuring the potential, but R labels the position of the charge distribution and is integrated, or so the final answer depends only on R. We should mention that 2.8 is rarely used in practice since the integral is so nasty unless the charge density rho is particularly simple. It is worth remembering mostly as a sanity check for the case of a point charge where rho r is almost equal to delta to the power of 3r. We will come back to this case below. The chapter of 2.1.3 integral from a Maxwell's equation. The third useful tool is Maxwell's equations themselves. Tau in a slightly different form. Using Gauss's theorem and Stokes' theorem, we can rewrite Maxwell's equation in integral form. Where Q int in the charge enclosed by the closed feature S and C is some closed curve. The first equation is known as Gauss's law, and the left-hand side is defined as the electric flux. The important implication of the Gauss's law is that regions that have no net flux in or out can enclose no net charge. Problems on the GRE that involve actually solving for realistic charge configurations always require the integral forms of Maxwell's equations. The differential forms, if they are ever needed, are mainly involved in the conceptual questions or questions that just require you to evaluate the divergence to occur given some electric field. There are always problems on GRE that involve simply solving for the electric field or electric potential of a charge configuration If a problem has a high degree of symmetry, for example, spherical, cylindrical, or planar, the fastest route is to use the integral form of Gauss's law. The recipe to calculate the field is simple and probably familiar from an electromagnetism course. The first is figure out the symmetry of the problem. Should the electric field point radially outward from a single point, spherical symmetry, radially outward from the central axis, which is such as cylindrical symmetry, or away from a plane, planar symmetry. This can usually be deduced from the shape of the charge configuration. The next solution is find a Gaussian surface. Visualize Gaussian surface S such that the electric field E is always either a perpendicular to S with constant magnitude or B parallel to S. This is where the symmetry is important, as you usually guess where the surface is based on the symmetry of the problem. You can see in the figure 2.4 example of a Gaussian surface over which the electric field from the charge line lambda is both constant and perpendicular. Now I want to go through the third section, solve for the field. The dot product E dot differentiation of the S then vanishes whenever E is parallel to S and is equal to the absolute of E differentiation of S over the rest of S. The constant magnitude, the absolute of E, can be pulled out of the integral and 2 point down reduces to as follow. Where R is the area on the Gaussian surface S perpendicular over which is perpendicular to the surface. We will treat several more standard applications of Gauss's law in the following section 2.1.4. Until the standard electrostatics configuration, thank you so much for watching my tutorial video. Today is 13th of April 2026. Time is 11:48 p.m.